Time for some practice. So we're going to be going through a practice exam for the second part of multivariable calculus, which has a particular emphasis on differentiation. Now, it's really important that you do practice because that helps you get comfortable with ideas and it helps you really see how ideas all fit together. So as much as possible, before you see the solution, try to do the problem first by yourself. And then you'll get to the most that you can out of it. We have 10 problems. There will be 6 multiple choice and 4 long answers. Lots of fun stuff ahead. Let's begin. Our first problem. And we have a picture. Below is the contour map. Now, a contour map is a collection of level curves. For the function f of xy, for 0 less than or equal to x less than or equal to 6, and 0 less than or equal to y less than or equal to 6. We're told that f of 0y equals y, and determine the value of f of 4, 2. Now, in particular, f of 0y equals y says we don't know much about the function, but we do know what's happening there. So 0y is the y-axis. And so we know how to evaluate the function on the y-axis. So that's something. Now, what are we after? Well, we're after the value f of 4, 2. Now we're told x goes from 0 to 6, and we have the grid. I've darkened the grid a little bit because the camera resolution sometimes is a little bit not as sharp as we'd like. And so we can mark. So here's 0, 1, 2, 3, 4, 5, 6. Then we have 0, 1, 2, 3, 4, 5, 6. Oh, that's very convenient. Almost as if they planned it. And they did. This was planned. Nice. Good job. Now, where's 4, 2? So x equals 4, y equals 2. That's this point right there. All right. Well, how do we answer it? Because we only know what's happening over here, not what's happening there. So we're going to take advantage of knowing things. We know that we have level curves. And what's the key idea? Level curves have the following fact, and that is equals function is constant. So in other words, if I'm on a level curve, the function is always constant on that level curve. So we notice that 4, 2 has a level curve. So what we can do is we can highlight that. So we're going to just go around here. And we're marking all our points. So as we follow this curve, we can say, look, the value that we're after has to be equal to the value at any point along this level curve. So, is there a convenient point for us? Yes. And so, in particular, we say, hey, f of 4, 2 is equal to that point right there, f of 0, 4. This is because they're on the same level curve. Level curves, you get the same value. We're constant on there. But for f of 0, 4, we know the answer is 4. So our answer is 4. Just follow the level curve, and there you go. All right, well, that's a nice warm-up one, right? Testing us. Do we know level curves? Yes. Yes, we do. All right, on to number 2. Let h of xy be a differentiable function. This means we can take partial derivatives, and it's smooth. All right. Given that the directional derivative of h of xy at 3, 1 in the direction 1/5, 3, 4 is 15, and the directional derivative of h of xy at 3, 1 in the direction 1/5, 4, -3 is -10, then what is the directional derivative of h of xy at 3, 1 in the direction 1/13, negative 12, 5. Now, we have three vectors here. Let's take a look at them for a second. And we have 1/5, 3, negative 4, 1/5, 4, negative 3, and 1/13, negative 12, 5. And if these numbers sound familiar, 3, 4, 5, and 5, 12, 13, that's because they're Pythagorean triples. And in particular, that means these are nice numbers. These are all unit vectors. 3 squared plus 4 squared is 25. And then divide by 5 squared, which is 25. That's 1. 4 squared is 16 plus negative 3 squared is 9. It's 25. Divided by 5 squared is 1. 12 squared, 144. Plus 25 is 169. Divided by 13 squared, which is also 169, is 1. All right, so we got unit vectors. Nice. That makes our job a little bit easier. We know that this is going to be something involving directional derivative. And you might say, well, how do you know that? Well, it says directional derivative. So that's a pretty good clue, right? But in general, if you see something with the direction and something that says derivative or equivalent word like rate or it's the change, then, okay, directional derivative is in play. So, given that we have a directional derivative, we can start by writing down the basic formula. So the directional derivative in the direction u of the function f at a point P is the gradient of the function dot u. All right, so what do we have? We have two directional derivatives. So what can we do? Well, let's write down the information. And for us, our function is called h instead of f, but we can say, well, okay, let's say our gradient of our function h at P, we'll refer to it as a comma b. It's going to have two entries because it's a function of two variables. And, okay, so we have two cases. When u is 1/5, 3, 4, then we have the following. The directional derivative is 15, so that's that. That's equal to the gradient, a comma b, dot the direction, 1/5, 3, 4. All right, now the other one. If our u is 1/5, 4, negative 3, all right, what is that? Well, the directional derivative is negative 10, and that's equal to our gradient, which we don't know, dot our direction, 1/5, 4, comma, negative 3. Now, what do we actually have? Well, if we carry out our dot product, well, we get 1/5 times a times 3, so that's 3/5 a. And then b times the 1/5 4 plus 4/5 b. And down here, we're going to get 4/5 a and minus 3/5 b. And we say, this is two equations, two unknowns. We can solve for a and b. And, that's the whole point. By using information about the directional derivatives, we can build up our gradient. And then once we have that, then we just apply the formula. Okay, so now our new plan. Okay, so we're going to solve for a and b. That's our plan. Well, let's rewrite this formula. So I'm going to multiply both sides by 5 in both equations just so we can get rid of fractions. So we get 3a plus 4b. All right, this is equal to 5 times 15. That's 75. Here, 4a minus 3b is equal to minus 50. Okay, And, well, let's suppose we want to get rid of the b's. What can we do? Well, one thing we can do is we can scale both equations in a nice way. And so I want something that both 4 and 3 divide into 12. So we'll multiply the first equation times 3, the second equation times 4. That'll give us a 12b and a minus 12b. And if we do that, we'll get 3 times 3a, that's 9a, 4 times 4a, that's 16a. So together that makes 25a. The 12b and minus 12b cancel. And then we get that's 3 times 75 minus 4 times 50. Well, everything has a factor of 25. So we'll divide everything by 25. And if we do that, we get a. Well, 75 divided by 25, that'll be 3. So 3 times 3, and 50 divided by 25 is 2. Minus 4 times 2, and that's 9 minus 8, 1. So a is 1. Well, now we know a, we can get b. So let's just put in a equals 1. 3 plus 4b is equal to 75. And, well, we're running out of space, but that says 4b is 72. Or, if we divide by 4, we get b is 18. Aha. All right. Good. Good. So, our gradient at our point. And the gradient determines everything in direct derivatives, right? It tells us like our tangent planes. It gives us our directional derivatives. Everything builds off of gradients. So our gradient looks like 1, 18. Now we can double check to make sure that the numbers work. Okay, 3 plus 72 is 75, no surprise. 4 minus 54 is negative 50. All right, so we're looking good. Now we're not done yet, but now that we solved for a and b, we're ready. So, our last step, we're going to plug in our directional derivative for that vector. So now we're going to let u be 1/13, negative 12, 5. Okay, so we're going to take our gradient, AB, 1, 18, dot 1/13, negative 12, 5. Now, what is that? That's 1/13, and then do a dot product. Now remember dot products. We have to remember dot products are very useful tools. 1 times negative 12, it's negative 12, so we're multiplying the entries. 5 times 18, well, that's 90. So negative 12 plus 90. Well, that's 1/13 times 90 minus 12, 78. And does 13 go into 78? Yes. Ha! It's like it was planned, because it was. It goes in 6 times. So we're looking for 6. There we go. The answer is E, 6. Nice. Cool. Cool. So this is a fun one. It tests, okay, if we have lots of directional derivatives, can we reconstruct the gradient? Hey, now that you have the gradient, find a new directional derivative. And yeah, so that's this is nice. It really helps us test, do we understand how directional derivatives work? All right, well, let's move on to number 3. Given that f of x, y, z equals a is a smooth surface. Smooth in the sense that what? It just means we can take derivatives. And that at the point 1, 5, negative 2, so that's the point on the surface, the tangent plane to the surface is 6x minus 7y plus 3z equals 11. Then find partial z partial x at 1, 5, negative 2. All right, so how do we proceed? Now, I can tell you there's a couple ways this can be done. So let me tell you the way that they want you to do it, and we'll work through that. And then I'll tell you a way that you could do it. It's a little bit more straightforward. All right, so this is sort of like what the Calc constructors intended. What was intended? We'll call it that. So here's what we do. We say, well, what's going on? We have the case f of x, y, z equals 8. And notice that what does this do? Well, this is like an implicit function. It defines defines z as a function of x and y implicitly. And in particular, you say, well, okay, so what we're really thinking of is we're saying, z is really a function of x and y. So when we look at this right-hand side, we say, well, okay, f depends on x, y, and z, but z depends on x and y. So starting with f of x, y, z equals 8, we can do the following. We say, all right, we'll take a derivative. And so we're going to take a derivative with respect to x. Now, why with respect to x? Because you see this partial x there. So another way we could have written this is saying take the derivative with respect to x of z and then evaluate that. So remember, this bar with a number, or in this case a point, means we're evaluating. All right, so we're going to take the derivative with respect to z. So I'm making a little note here, take the derivative with respect to z. With respect to x, I know words. I can pay attention. I'm sorry about that. Let's be careful here. All right, so doing a quick taking derivatives here, we have derivative of f with respect to x, so that's f sub x. And then we have derivative of f with respect to z, so that's f sub z times partial z partial x, right? Because what do we see? Well, we see there were 2 times that x shows up. So we just have to go down our 2 paths. Now that's equal to the derivative of x on the other side. Derivative of a with respect to x is 0, because it's not changing, it's a constant. And so, in particular, we say, partial z partial x is equal to, you subtract the f sub x, divide by fz. So you end up with minus fx over fz. Now, this is a formula that you can memorize if you're young and you have lots of room left in your memory banks. You'll notice something here. See how this z here, that's upstairs, then that derivative of z goes downstairs. And on the other hand, the x that's downstairs here, that x is upstairs there. So you sort of swap and throw in a minus sign for good measure. So if you have a function equals number, you can do this to take any partial derivative you want. Now, that's the generic formula for implicit differentiation. How does that tie in? Well, what do we have? We have something pretty nice. We have, I'm trying to pick, I just love highlighting things. We have a tangent plane. And one of the things that comes with a tangent plane is a normal vector. How do you find the normal vector to an implicit surface? The gradient. Now, quick question. Is the gradient of our function at 1, 5, negative 2, which, by the way, that is f sub x, f y, f z, is that equal to 6, negative 7, 3. And if not, why not? Okay, now here's where it gets dicey. It could be, but probably not. Here's what you have to remember. Normal vectors are not unique. So just because we have a normal doesn't mean, it's the normal that we need. But what is true is that all normal vectors are parallel. So it's some multiple. All right, so we throw in some multiple, we'll call it lambda. And now we say, we're almost there. Come down here. What do we see? F sub x would be 6 lambda, right? Because the lambda goes through. So we get a minus 6 lambda. And what about fz? Well, that would be, again, we go through, that would be 3 lambda. Minus 6 lambda over minus 3 lambda gives us negative 2. And that's the answer. There we go. Now, that's what was intended. But we can do it in a completely different way. Okay, so here's the sort of the fast way to do it. The fast way to do it is to say, what can we do? We can say, hey, I don't know what the surface is, but I don't need to know. What I can do is say the tangent plane to the surface can act as our stand-in. So we're going to use a tangent plane as a stand-in for our f of x, y, z. Okay? That's the whole idea. And we say, we know that this can replace our function. And I said, well, how do we know that? Well, because the whole point of tangent plane says I'm mimicking the function. So if we can answer the question with the tangent plane information, that says whatever the answer is has to be the same as if the function were the tangent plane. Now, word of caution, great strategy for multiple choice. For long answer, people would be like, you got to think about that. We'll give you some partial credit, but not all. But for multiple choice, just say, hey, if I don't know the function, but they give me the tangent plane, use the tangent plane for your function, and you'll get the right answer. So, what is that? Well, what it says is, hey, we can use the following function. We can say 6x minus 7y plus 3z equals 11. But, more importantly, what can we do? Solve for z, right? So, solve for z. So, we're going to move stuff across and divide. So, we get 3z is equal to 11 minus 6x plus 7y, or z is 11 thirds minus 2x plus 7 thirds times y. Now, in this form, if we have this tangent plane given to us, we can read off information. The coefficient of x, this coefficient stores the derivative of z with respect to x. And this coefficient here, this stores the derivative of z with respect to y. That's what tangent planes do. They're storing information. They store the value of the function, and they store the derivatives with respect to x and with respect to y. And then we say, oh, well, I need to know the derivative of z with respect to x, so it's this coefficient in front of the x, so the answer is negative 2. And we're done. And so they both work, and they both got the same answer, because there's going to be a consistency. And so you have choices, right? When you're doing multiple choice, you have a little bit of freedom. It's like, okay, how do I get to the answer efficiently? Or how do I eliminate non-answers efficiently? So, all right, that was a fun problem. I actually like this one. And I like that we have different ways to do it. All right, number 4. We're given that g of xy is a differentiable function, so okay, we can take derivatives. G of 0, 0 is positive. And z, which is 9 plus 6x minus 12y, is the tangent plane to not to g of xy, but to g of xy quantity squared at 0, 0. Then, which of the following is a tangent plane to g of xy at 0, 0? Ooh, interesting, interesting. Okay, all right, now, let's talk about what we know. When we talk about tangent planes, we say, hey, tangent planes are storing information. So, what does a tangent plane store? And in particular, it stores information about the function and about derivatives. So, when we write down that z is equal, and we're going to take advantage of the fact that we're at 0, 0, z is equal to 9 plus 6x minus 12y. This 9 here, that's the value at 0, 0. And I'm talking about the value of g, because that's the tangent plane to g. This 6 is, that's g sub x at 0, 0. And this negative 12, that's g sub y of 0, 0. All right. So we have that information. So let's think about what does that tell us. Let's start with g of 0, 0. Well, we can come here and we can say g of 0, 0, that's equal to little g of 0, 0 squared. But we also know that g of 0, 0 is equal to 9. So g of 0, 0 is plus or minus 3, because we can take the square root of both sides. No, we were told something. G of 0, 0 is positive, and so since g of 0, 0 is positive, then that really says, hey, g of 0, 0 is the plus 3. All right, so we have some information. Not enough, because we got to have everything to make a tangent plane. All right, but this is what we're given, and let's write down what we're looking for. We want to find g of 0, 0 plus g little g at 0, 0 times x plus gy 0, 0 times y. So we now know that that is a 3, which doesn't do much for us. Okay, all right, no surprises. We could have told you it was a 3 just by looking at the choices. But let's go deeper, a deeper cut. Let's take g sub x at 0, 0. So in particular, we know g of xy is g of x comma y squared. So we have the function g of xy inside the square function, a function in a function. So what would capital G sub x look like? Well, we're taking the derivative with respect to x of g of xy squared. So chain rule. So the outside is the square function. So that becomes 2. And then you have your g of xy to the 1 times the derivative of the inside. So that's the derivative with respect to x of g of x comma y. Or, written more simply, that's 2 g of x comma y, g sub x of x comma y. Now, we'll plug things in. We know g sub x at 0, 0 is 6. So 6 is equal to g sub x at 0, 0, which is equal to 2g at 0, 0 g sub x at 0, 0. Now, do we know things? Yeah, we know that g of 0, 0 is 3. Wahaha! And 2 times 3 is 6. So that's 6 gx 0, 0. Well, 6 equals 6 times what we're looking for. So g sub x at 0, 0 is equal to 1. So that says this part is a 1. All right. What has a coefficient of 1? Just the single option. So we now know the answer is D. We're done. But for completion's sake, let me switch here. Mike, one more note. If we did the same thing for g sub y, well, we can run through the same argument. And what you get is that g sub y of xy, okay, that's derivative with respect to y of g of xy squared. Again, it's a chain rule, 2g of xy times the derivative with respect to y of g, right? So, plug in, and we get g sub y at 0, 0, which, by the way, we know is negative 12, but it's also equal to 2 times g of 0, 0, which is 3 times, whoops, I put an x here. I should have put a y. I'm sorry about that. Times gy at 0, 0. Well, now divide both sides by 6, and we get gy of 0, 0 is negative 2. Right? Good. So there we go. There we go. We did it. We did it. Essentially what's happened is we said, I can tell you the tangent plane to the square. Can you tell me the tangent plane to the original function? And so that's what was going on. And so yeah, you have to be careful. You know, there are certain tempting answers. It's just like, oh, look, you divide by 3. All right, divide everything by 3. All right, that was an option. Or it's like, oh, take the square root. Take the square root of all the pieces, right? So there'll be some tempting options, but be careful. Be careful, right? We know what you might be tempted to do, and so think it through. Make sure it's right. Okay. That brings us to number 5. A function capital F of xy has the following second-order Taylor polynomial at the point 3 minus 1. All right, so what do we have? P2. So if you see this notation P sub 2, the 2 here is referring to the order, and so it's a Taylor polynomial, that's P for polynomial, 2 for second order, of xy, is 11 plus 3 times x minus 3 squared, plus 9 times x minus 3 times y plus 1, plus 7 times y plus 1 squared. All right, now notice, why do we have x minus 3's and y plus 1's? Because that's where we're at, 3 minus 1. All right, so what's going on? Well, the key idea is that this is storing derivatives. In particular, it's storing up through second order derivatives. All right, so now we know everything up through second order for the derivatives. Okay, so we can make a little note here. Taylor polynomial is storing derivatives. And you have to be careful, only up to the order. Up to the order. In this case, we're second. So, what can we do? Well, we can read off our values. Like f of 0, 0 is the 11. Now, what about f sub x at 0, 0? Well, notice that there's no x minus 3 term. Well, that means that coefficient has to be 0. Fy at 0, 0, again, there's no y plus 1 term. So that says that coefficient is 0. And we say, oh, we see that derivative with respect to x, and I'm so sorry. I did this again. It's not 0, 0. Sorry, I just got off a problem that did 0, 0. This is 3 minus 1. Come on. Come on, we can do better. And the good news is, multiple choice. They won't catch our silly mistakes like that. Okay, at 3 minus 1, we see that since there's no x minus 3 term or y plus 1 term, those terms have to be 0, which means the gradient is 0. And so we say, aha, the gradient of f at 3 minus 1 is 0, so a critical point. All right, good. Well, that rules out A, because A says, hey, this is not a critical point. All right, well, what's up next? Now that we know it's a critical point, we go into classification. And for classification, what do? Well, there's a test. There's the second partials test. And we'll keep making a list here, but I want to make the second partials test, write it down for reference. So you compute this quantity, fxx, at your point P, so 3, negative 1, fyy at the point P, 3, negative 1, minus fxy at the point P, 3, negative 1, squared. And now we say, well, if that quantity is negative, then we're at a saddle. If that quantity is positive, we split it into two cases. If fxx is positive, we're a local min. And if fxx is negative, we're at a local max. Now, the good news, all this is essentially stored in our formula sheet, so you don't have to remember all the fine details. If it equals 0, inconclusive. We don't know what's going on. Okay, so there's our second partials test. So we need our second derivatives. And good news, we have our second derivatives. Why do we have our second derivatives? Because we have our second order Taylor polynomial. Okay, so we keep going here. Now, what is fxx at 3, negative 1? So we're looking, see how we have xx? So we're looking for the term that has the x squared piece to it. We say, what's the coefficient? Now here's the part where you have to be careful. Is this fxx, and why not? It's almost fxx, right? It's really tempting. But you have to remember, it's that coefficient divided by 2. That's what shows up here. So there's this sort of careful divide by 2 thing going on. All right, so really, fxx at 3, negative 1 is 6. In a similar way, fyy, 3, negative 1, because it's fyy, you need to divide by 2, and that's 7. So this coefficient is fyy divided by 2. Or, say, okay, that says fyy at 3, negative 1 is 14. And, all right, what about fxy at 3, negative 1? Well, that's 9. No division needed. So be careful, right? Be careful. Know how a Taylor polynomial is put together. And the main thing to remember is that the Taylor polynomial stores the derivatives. Another way to say it is if I take derivatives of the Taylor polynomial, it matches the derivatives of the function. So if I want to find the derivative with respect to x, take the derivative with respect to x and evaluate. That's the right answer for f. How about second derivative with respect to x? Take two derivatives with respect to x twice, evaluate. That's the right derivative, right? So it's storing all that information. The thing you just have to be careful about is what's happening with these two coefficients, because there's this sort of hidden over 2 that's easy to forget about. When in doubt, take derivatives, you'll be okay. Now, we're ready. Here we go. We say the value we're interested in, this value here, is going to be 6 times 14 minus 9 squared. 6 times 14 is 84. Minus 9 squared is 81. That's 3. Now, we don't care about the size of the number. It's the sign that matters. We saw the sign, and it opened up our eyes. We saw the sign. What is our sign? Positive. So this is positive. Okay, so that means we're either a local min or a local max. Cool. But which one? Got to go deeper, right? Okay, so we've ruled out saddle, and we've ruled out inconclusive. Now, the last thing is to say, now we narrow it down. Look at fxx and fyy. Look at the sign. We say, well, they're both positive. They'll have to be the same sign. So, if they're both positive, we are a local min. So, our answer is C. Our critical point is a local minimum. All right, so this is fun. This is combining two important ideas: Taylor polynomials, storing derivatives up to the order, and second partials test. And I will say, second partials test is a very popular question. They love throwing something on there. And, they put it on the formula sheet. They're really invested in it, right? So make sure you know how to do it. Make sure you understand what Taylor polynomials are doing, storing our derivatives. All right, that brings us to our last multiple choice. Oh, my goodness. Feels like we just began. No, it doesn't. We're going slow. We're taking our time. We're thinking about concepts. So no problems. Number 6. What is the maximum rate of change equals maximum possible value of a directional derivative for this function h of xy, which is 3x squared y minus xy cubed plus x minus 8y at the point xy equals 1, 1. Now, what is this question asking us to do? Well, when you see maximum rate of change, and it even explicitly spells it out, maximum value of a directional derivative, what that is trying to do is it's saying, hey, do you remember what the gradient does? So this is testing us on properties of the gradient. All right, so we say, okay, so what are the properties of the gradient, since it seems to want to ask us about that? Well, the max rate of change is equal to the magnitude of the gradient. The direction of max rate, well, that's equal to the gradient. Now, oftentimes for direction, they'll make it into a unit vector, and to make something into a unit vector, you divide by 1 over the magnitude. Now, what if you want the max rate of decrease, right? So max rate of change is like positive. You could say the max decrease, well, that's negative the magnitude of gradient, and the direction of max decrease is negative the direction of the gradient. So that's our properties of the gradient. Okay, so we're after the maximum rate of change. In particular, that tells us that we really are after this expression. We're after the magnitude of the gradient. So we say, okay, cool. And now, no funny business. They explicitly gave us the function. And so we say, well, let's start by taking the gradient of our function. And so that's our collection of partial derivatives. So when we take the derivative with respect to x, treat y like a constant. We'll get 6xy minus y cubed plus 1, comma. Take derivative with respect to y. Treat x like a constant. 3x squared minus 3y squared minus 0 plus 0 minus 8. So the gradient of h at the point 1, 1 is 6 minus 1 plus 1. So that's the nice thing about plugging in 1, 1. It's the coefficients, comma, 3 minus 3 minus 8. Well, that's 6 minus 8, right? Because here the 1's cancel, here the 3's cancel. So we're almost there. Take the magnitude of what we just found. And what do we get? Magnitude of 6 negative 8. Well, that's the square root of 6 squared plus negative 8 squared, which is the square root 36 plus 64, or square root of 100, which is 10. C. Our option, our answer was C. Ah, good. Whew, what a great test. Wait, what? There's more? Oh yeah, we just did the multiple choice. We still have the workout problems. All right, so we start. Now, some notes. On the multiple choice, only the answer is being checked. So you can take some shortcuts. You don't have to show your work. On the workout problems, you have to show your work and make sure you're answering the question that they ask you. So it can take some more time. Be patient. Make sure you got everything they asked for. So with all that said, number 7. We have the following information about the functions, f, u, and v. So f is a function of x and y, u and v are functions of s and t. So we have the value of the functions at 1, 2, and we have the values of the various partial derivatives at 1, 2. Everything's there, nice and clean. We also are going to make a new function, g of st equals f of u of st, v of st. Now notice, what do you see? When you see functions and functions, you're like, function and function, that is almost always pointing to a chain rule. So without even thinking about what's coming, we're starting to put our mind into our chain rule mindset. So, part A, use the chain rule. I told you it was coming. We knew it. All right, use the chain rule to give expressions for g sub s of st and g sub t of st in terms of the functions f, u, v, and the appropriate derivatives of those functions. And for the final answer to this part, write the full expressions in terms of s and t. Okay, so here we go. What's going on here? Well, I like to start by making a tree. It's going to help me understand how all these things relate. So I see f. F is going to depend on u and v. Okay. Well, I really should say x and y. That's what I should say. And x is what we're calling u, y is what we're calling v. All right. But now, what do these depend on? They depend on s and t. All right. So, if I want to understand what's happening when we talk about the derivative with respect to s. All right. Well, in that case, we have some pieces. Now, I'm going to mark these derivatives here. We have our f sub x, u sub s, u sub t, f sub y, and v sub s, and v sub t. So, g sub s, I'm looking at where do I see some s's. I see 2 of them. So I have to go through 2 paths to get to the s's. So g sub s is f sub x, how does the function change with respect to its first entry, u sub s, plus f sub y, v sub s. Now, in the interest of full disclosure, I should say, I should have made this a u and a v, made that a u and a v. I apologize for any confusion, but the spirit of it is here. Okay, now that's g sub s. Do the same thing, but for t. Okay, there's 2t, so we have 2 paths down. So g sub t is, well, we have our f sub x, and our u sub t, and our f sub y, and our v sub t. Now that's a really shorthand notation. And normally that's where we'd stop. But they asked us for one more thing. And they said, hey, you know what? When you're doing this problem, for the final answer to this part, write the full expressions in terms of s and t. So what we're doing here is we're suppressing our of things, right? So really, this is g sub t says g sub t is a function of s and t. And so we're going to put it all on the table. So we're going to rewrite this, but spell it all out in small letters, because otherwise we'll run out of space. So we have g sub s of st. Well, that's f sub x. Now, f depends on u and v. So f sub x, u of s comma t, v of s comma t. Right, that's f sub x. U sub s, well, u is a function of s and t. So it's really u sub s, st. So that's f sub x, u sub s, but all spelled out. Add to that the second term. Well, the only thing that really changes is this subscript for x becomes a y. So we have f sub y, and we have u of s comma t, v of s comma t. And then this u sub s is becoming a v sub s. So that's the first part. That's your g sub s. And now do the same thing for g sub t. All right, so we get our fx, u of s comma t, v of s comma t, times our u sub t of s comma t, plus our f sub y, u of s comma t, v of s comma t, times our v sub t of st. All right, so that's part A. Done. All right, so part A, straightforward chain rule. No surprises. Part B, find the tangent plane. Okay, so what do we need to get the tangent plane? Well, we need a couple of pieces of information. So for part B, we need to find what is g of 1 comma 2, right? Because we need that value. We also need g sub s at 1 comma 2, and we also need g sub t at 1 comma 2. Now g of 1, 2, that would be f of u of 1 comma 2, v of 1 comma 2. But what is u of 1 comma 2? It's 1. V of 1 comma 2 is 2. So that's f of 1 comma 2, which is 4. Okay, so that's g of 1 comma 2, 4. All right, g sub s. It's all stored right here. That's why they had it spell us out in excruciating detail. Now we're going to take advantage of what we did here. U of 1 comma 2 and v of 1 comma 2 is 1 and 2 respectively. So this is equal to f sub x at 1, 2, u sub s at 1, 2, plus f sub y at 1, 2, v sub s at 1, 2. So we come up to our chart. We have 3, times -2 plus -1 times 5. So that's -6 minus 5, which makes -11. All right, g sub 2, similar process. We're going to evaluate. We'll get fx at 1, 2, u sub t at 1, 2, plus fy at 1, 2, v sub t at 1, 2. So, start filling in. Fx at 1, 2 is still 3. Ut at 1, 2 is 6. Fy at 1, 2, still -1. And Vt at 1, 2 is -3. So you get 3 times 6 is 18. -1 times -3 is 11. Sorry, is 3. Sorry, I'm getting ahead of myself. 18 plus 3 makes 21. I saw an 11. All right. Be careful, right? Now, we know the value. We have the value of the partials, first order partials. We put it together. So our tangent plane, which is our linearization, well, that's g of 1, 2 plus g sub s at 1, 2 times s minus 1 plus g sub t at 1, 2 times t minus 2. So we put those numbers in. We're going to get g of 1, 2 is equal to 4. And then g sub s is -11 times s minus 1. And then plus 21 times t minus 2. All right. So that's part B. The tangent plane, also known as the linearization. Okay. So the last part, well, we say, hey, this tangent plane isn't just a tangent plane, it's a good approximation. So this is approximately g of s comma t. Now, it's only good near the point of tangency, near the point 1, 2. Well, hey, wouldn't you know it? That is near 1, 2. So we say, g of 0.97, 2.02 is approximately 4 minus 11. And now we're going to take 0.97 and subtract 1. 0.97 subtract 1 is minus 0.03. Plus 21 times 2.02 subtract 2. Well, that's going to be 0.02. Okay, so good news. A minus makes a plus. Okay, so that is good news. Whew. Okay, so everything's looking positive. So we end up with 4 plus 11 times 0.03 is 0.33. 21 times 0.02 is 0.42. If you add those together, 0.33 and 0.42, you get 0.75. So our estimate, what is the value of the function at 0.97, 2.02? It's about 4.075. Now you might say, gosh, that's kind of big, but keep in mind, look at these derivatives here. They're not non-trivial, right? They're substantial. And so we actually have a very steep, in some sense, tangent plane. So it's not an unreasonable answer. So that's good. And that's the process. That's what you need to be able to work through. And so tangent planes or second-order Taylor polynomials, both of those often show up in terms of estimates. And so we'll be ready for them should the need arise. All right. Number 8. find both. That's implying that there's two points on the surface, 2x squared minus y squared plus z squared equals 8x plus 20. All right. Where the tangent plane is parallel to 4x minus 4y plus 6z equals 5. Ah, okay. Interesting. So we have this surface. Now, it's not a surface of the form z equals f of xy. It's a surface where we say, hey, it's like an implicit surface. Now, this might feel kind of familiar. And you say, it feels kind of like a hyperboloid of one sheet. And that's because it's a hyperboloid of one sheet. There's been a small shift. That 8x does a small shift, but it's a hyperboloid of one sheet. You don't need to know that to answer the question. It's just a fun fact, and we love fun facts here. All right, so what's our strategy? Well, one thing is to start thinking about, how do these things connect? We have a tangent plane, and we have this implicit surface. We say, well, how do those things tie together? And it's one of the most popular questions on this type of exam, which is to say, oh, if I give you an implicit surface, give me a tangent plane at a particular point. So how does that process unfold? Well, first thing you need to do is move all the variables to one side. So this 8x, I want to move it across so that it's joining the other variables. And let's go ahead and put it with the x variable. So we have 2x squared minus 8x minus y squared plus z squared equals 20. You can move the 20 across, but you don't need to. The important thing is that this side is a number. It doesn't have to be 0. Any number will do. And we're going to think of this part as our function of x, y, z. And now, the great aha, which we've already alluded to, is to say this connects to normals for tangent planes. And that is that the gradient of f at a point P on the surface, for P on the surface, we're going to spell this all out, is a normal for a tangent plane. Now, you're probably like, boy, Steve, why did you go to great lengths to underline the word A? Is that like a clue? All right. So, let's now take our gradient. So we have our capital F. We take our gradient. We say our gradient will become 4x minus 8 minus 2y plus 2z. So here's our gradient. Now, what do we want? Well, this is a normal to our surface, right? We want it to be parallel to this plane. Now, for this plane, we can read off its normal, 4, negative 4, 6. So we have these two vectors. What's true about these two vectors? If we want the planes to be parallel, what's true about their normals? The normals are parallel. Ah, okay. Now, does that mean that the normals are equal? No. That's where you have to be careful. But it does mean that they're close, in the sense that one is a multiple of the other. So let's go ahead. We'll have lambda. Lambda here is just standing for, it's a multiple of. All right. Good. So if we see what this says that at such a point, we have that 4x minus 8 is equal to 4 lambda. And we have minus 2y is equal to minus 4 lambda. So I'm just, comparing entry-wise. 4x minus 8 is 4 lambda. Minus 2y is minus 4 lambda. And 2z is 6 lambda. And there's one other fact. The other fact is we have 2x squared minus 8x minus y squared plus z squared equals 20. All right. Now, with all of this in place, all that we have here, what do we do? Well, it's one of those things we should think about for a moment. We want to solve for points. So that's good. We have to solve for points. Here's what we can do. Notice in this equation, I just have x and lambda. Here I just have y and lambda. And here I have z and lambda. So let's solve for our x, y, and z. So what is x, what is y, and what is z? Well, starting here, I divide. Z is 3 lambda. Y, divided by negative 2, 2 lambda. Now here, I would divide by 4, so that's x minus 2 equals lambda, or x equals lambda plus 2. Now notice, I have x, y, and z in terms of just one symbol, lambda. And we say, idea. What if we take this information here and plug it into our surface? Then we get one equation and one variable, lambda. Once we solve for lambda, we're done. All right, so we need 2 times lambda plus 2 squared minus 8 times lambda plus 2. Okay, so I'm just, everywhere I see x, I put lambda plus 2, minus y squared, 2 lambda squared, plus z squared, 3 lambda squared, equals 20. Okay, one equation. Let's see what we can get. So this will become 2 times lambda squared plus 4 lambda plus 4. And here, I'll go ahead and distribute that through. Minus 8 lambda minus 16. Square this, minus 4 lambda squared. Square here, 9 lambda squared equals 20. Okay, distribute. 2 lambda squared plus 8 lambda plus 8 minus 8 lambda minus 16 minus 4 lambda squared plus 9 lambda squared equals 20. Oh, my goodness, can we solve that? Well, we can simplify. 8 lambdas cancel. Well, that's convenient. 2 lambda squared minus 4 lambda squared plus 9 lambda squared. All together gives us 7 lambda squared. On the other hand, I can move this across. I add 16. That makes 36. I subtract 8. That makes 28. Or lambda squared is equal to 28 divided by 7 is 4. Or lambda is plus minus 2. So now we know the values for lambda. But as soon as we know lambda, what can we do? Get the x, y, z. And for those x, y, z, we are parallel. And we are on the surface. So now the last thing for us to do is plug in. So we get 2 points. So we have our lambda equals 2 and our lambda equals minus 2. So for lambda equals 2, 2 plus 2 makes 4. 2 times 2 makes 4. 3 times 2 makes 6. So point number 1, 4, 4, 6. Point number 2, negative 2 plus 2, 0. 2 times negative 2, negative 4. 3 times negative 2, negative 6. And so 0, negative 4, negative 6, that's our second point. And we are done. We found both the points. Wow. Good, 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 good. And so here, this one is kind of an interesting one. It's like, well, it's a little different. But being different isn't bad. We like to see different problems. It helps us think in new ways. And so for us, it was, hey, how do we take the fact that we have these 2 points where the tangent planes are parallel? Oh, it just means that our gradient has to be some multiple of that normal. We say, okay, well, that gives us some equations, and now let's solve. And by the way, you can say, these equations are going to feel really familiar after we do the next couple of problems. Well, that's all right. These are good ideas. We use them over and over and over. All right. On to our next problem. Number 9. Find the absolute max and absolute minimum for the function h of xy is xy squared minus 4y, closed and bounded region, y squared less than or equal to x less than or equal to 4. Also indicate the points at which the absolute maximum and minimum occur. All right, so there's some clues here. We see absolute max and absolute min. Now that's a clue. It doesn't necessarily say for sure what we are, but we also see this closed and bounded region. That's a really big clue, but there's one more really big piece. So when we're looking for it, the question is, do we include the interior or are we just on the boundary? When we see our formulas here, they both involve a less than or equal to. That says we're including the inside. So this is our making a list. So we are going to do our make a list strategy. All right, so we'll go through and talk about that in a second here, but let's start by looking at what this region looks like. And so we have 2 bounding curves. One of them is the curve x equals 4. That looks like this. And notice we are to the left of x equals 4 because x less than or equal to 4. Then we have this x equals y squared. Now that looks a lot like y equals x squared, but we just sort of turn it on the side. So we have this parabola. So this is y squared equals x, x equals y squared. We are going to be to the right, right? X is bigger than or equal to that. And so I have to be to the right of the parabola, but to the left of this line, which means that our region is this part right here. All right. Well, we start making our list. And I always say, throw in the corners automatically. In this case, there are 2 corners. You say, well, where are they? Well, we know the x values are 4, because they're on that line x equals 4. And so, okay. So if y squared is equal to x, y squared equals 4. So when does y squared equal 4? Well, at y equals positive 2, and at y equals negative 2. So we have our 4, 2, and our 4, negative 2. So just a reminder, these are our corners. Now, what else do we need to check? Well, we have to check the interior. So the interior check, that's one where we say, well, what point could look like a potential absolute max or absolute minimum? Where could it occur? And for that, we say, look at where the gradient equals 0. So here's our function. And we say, well, that says we need our, take the derivative with respect to x, y squared, and that's it, comma, take the derivative with respect to y, 2xy minus 4. All right, that has to equal 0, 0. Now, we get 2 equations. One equation says y squared equals 0, and the other equation says 2xy minus 4 equals 0. Now notice this equation, y squared equals 0. That's a pretty straightforward one to solve for. That is y equals 0. All right. Well, great. Loving it. Loving it. Well, if y equals 0, throw that into this equation, and what do you get? We end up with the conclusion that negative 4 equals 0, right? Because you have 0 minus 4 equals 0. Well, where does negative 4 equal 0? Nowhere. And so like, wait, what? What does that mean? Well, it means that there's going to be no interior points on our list. So sometimes when you go to check, hey, where does the gradient equal 0? The answer can be, it never equals 0. That's a perfectly valid possibility. That's okay. That's okay. Now, do you still have to do the check? If you want points, absolutely. But keep in mind that things can happen. Okay, so we've gotten our corners. We've checked the interior. That leaves our boundary curves. So we have two boundary curves. Let's go, and it doesn't matter which order we go in. Let's suppose we start with x equals 4. All right. So then our curve will become h of x comma y. Well, h of x comma y equals h of 4 comma y, right? I'm using x equals 4. So everywhere where we see the x, we put a 4. So that becomes 4y squared minus 4y. All right, take a derivative. And right, because this right here, this is some function of y. So we say, well, the derivative of this function, that's 8y minus 4. Set that equal to 0. And, well, that says, oh, add 4, divide by 8, and we get that y is 1/2. So at x equals 4, we say, there's a potential at y equals 1/2. Well, that would be roughly here. Do we need to include it? Yes, it's a potential place. So that's on our list. So here, we'll throw it in 4 comma 1/2. Okay, so this is a boundary of x equals 4. Now, the good news is there's only two boundary curves, so this will be a relatively short one. The other boundary curve is x equals y squared. All right, well, what happens here? Well, our h of x comma y becomes, replace x by y squared, h of y squared comma y. Well, what is that? Well, we're going to get y squared times y squared. So that's y to the 4th minus 4y. Right? Replace x by y squared. So this, again, is some function of y. Take the derivative. What does the derivative look like? Well, that's 4y cubed minus 4. Well, okay, which is 4 times y cubed minus 1. Set that equal to 0. Well, when does y cubed minus 1 equal 0? At one point, right? That's when y cubed equals 1, or y equals 1. But remember, x is y squared. So our other boundary point will become 1 squared, 1 comma 1. Okay, so this is our boundary for x equals y squared. All right, so remember, we are in our make a list. So there's the song. We're making a list, checking it twice, gonna find out which points are nice. Absolute, max, and min are found. We've made our list. So let's check it twice just to make sure we didn't forget anything. Did we get the corners? Yes. Did we check the interior? Yes. Did we check each boundary curve? Yes. And now we say, look, our answer must be one of these. In other words, the absolute max and min has to occur at one of these points. So at this point, we now say plug it in. We're going to plug each one of these into our function. So here we go. And we can do these in any order. Some of them will probably be easier than others. I think 1, 1 is pretty straightforward. When we plug in 1, 1, you get 1 times 1 minus 4 times 1. That's 1 minus 4 is negative 3. Okay, well, what about the 4s? Now, in some sense, we can, of course, use just this expression, but, it shouldn't be too bad. So we get 4 times 2 squared, which is 4, minus 4 times 2. Okay, so that's 16 minus 8 makes 8. Here, we're going to get 4 times minus 2 squared, so that's still 4 times 4. Subtract 4 times minus 2, so that's going to become plus 4 times 2. So that's 16 plus 8, 24. Here, 4 times a half, so we're going to get 4. A half squared is a quarter, minus 4 times a half. Okay, that's 1 minus 2. 1 minus 2 is negative 1. And we've plugged it in. We're ready to look. We see a big number. That'll be the absolute max. We see a small number. That'll be the absolute min. Anything else in between is out. It is possible that the absolute max is achieved at multiple points. It is possible the absolute min is achieved at multiple points. If you're in that situation, make sure that you mark all the points involved, because it says indicate the points at which the absolute max and min occur. So here we go. We're ready to put our answer. We'll put it inside this box. Absolute max is 24 at the point 4, negative 2. Absolute min is negative 3 at the point 1, 1. And there we go. That's the answer. All right, good. Well, that's number 9. That leaves us with our final problem. One last problem. Number 10. Find the absolute maximum and absolute minimum for the function f of xy equals 4xy, given that x to the fourth plus 10xy plus 16y to the fourth equals 3. Now, a couple of notes. This is very similar to one that's been on an old exam, so there's nothing crazy here. But I do want to point something out, which is kind of cool. Oftentimes we do some of these problems and say, we could do this by just like, hey, solve for y, and then get down to a function of a single variable. In other words, like put on your Calc 1 hat. This, you can't do it that way. You really got to use the technology. So, hey, we really have gained something. We can do problems that we definitely couldn't do before. Now, what kind of problem are we doing? Well, we see some words in common with the last problem. In other words, you see words like absolute max and absolute min. But it's phrased slightly differently. We have this function f of xy equals 4xy, and that x to the fourth plus 10xy plus 16y to the fourth equals 3. Now, what's different between the previous problem and this problem? Notice that we have this equals versus less than or equal. In other words, the less than or equal says include the inside. This one says don't include the inside, it's just the boundary. So another way to think about it is we're like, it's kind of like the previous problem, but it's like, oops, all boundary addition. And so we say, okay, but hey, what does that really mean? Well, we're going to go through and do constrained optimization, but it's spiritually very similar to what we just did. In other words, we're making a list of where things can happen. Now, there is some subtlety. How do we know we get an absolute max and an absolute min? The process itself doesn't always guarantee it, but if it says it, just trust it. And I've been humming and hawing. I haven't actually said what this is. So let's say it together. On 3. 1, 2. Lagrange multipliers. Oh, God. Sorry, I couldn't help myself. Okay. Yeah, it's a Lagrange multiplier problem, right? So it's a constrained optimization. All right. Now, how does that work? So constrained optimization and Lagrange multiplier. Well, really, ultimately what's going to happen is we're optimizing this function f of xy equals 4xy given our constraint. And our constraint function is g of xy equals x to the fourth plus 10xy plus 16y to the fourth equals 3. What we want to build up to is we'd like to solve for x's and y's. So we need some equations for x's and y's. And we say, here, this is one equation for x and y. But we need a second equation. So that's where the method of Lagrange multipliers comes from. The thing to remember for that, so if you see an optimized function given something equals something, so you're in just the boundary, then you say, I'm going to look at gradient of f equals lambda gradient of g. So that's the thing to remember. Or that really says the partial derivative with respect to x equals lambda partial derivative of g with respect to x. Partial derivative of f with respect to y, that's lambda partial derivative of g with respect to y. Which, becomes, and I'm just going to say what this becomes generically, then I'm going to actually do what I would do in practice. Solve for lambda. So in the first equation, you get fx over gx. In the second equation, you get fy over gy. And now you say, well, hold on a second. This right here, because these both equal lambda, they must both equal each other. So this is a second equation for x and y. In other words, we get two equations and two unknowns. And so that's enough for us to solve and find points. Those points get on the list. Once we have the list, we plug it into the function. So, all right. So let's find this second equation. So, okay. I'm sorry. I'm saying the word "so" a lot. I'm debating about which version of blue pen do I want, or do I go with a purple pen? These are things that are important when we're solving problems. What's the right color? So I start with this equation. What is f sub x? The derivative of f with respect to x is 4y equals lambda g sub x. That would be 4x cubed plus 10y. And the derivative of 16y to the fourth with respect to x is 0. Second equation, f sub y, 4x equals lambda. Okay, g sub y. That goes away. Then we get 10x and plus 64y cubed. All right, and then I go through and I say, all right, solve for lambda. So we have 4y over 4x cubed plus 10y. That's from the first equation, equals 4x over 10x plus 64y cubed. And we don't like fractions. They're very scary for people. So we're going to do some cross multiplying. And that says, well, okay, we get 4y times 10x plus 64y cubed is equal to 4x times 4x cubed plus 10y. Distribute 40xy plus, oh, these are getting big numbers, 4 times 64, 256y to the fourth. And then here, 4 times 4, that's 16, x to the fourth plus 40xy. And you might get nervous, but remember, if you've lived a good, clean algebra life, nice things are going to start happening. And what are some nice things here? The 40xy's cancel. Nice! Turns out 16 can go into 256. And in particular, 256 is 16 times 16. So if you divide, that becomes 16. So we get, aha, x to the fourth, and 256 became 16, and 16 is actually 2 to the fourth. So that becomes 2y to the fourth, which leads us to x equals plus or minus 2y. Yes, be careful. Plus or minus, not just the 2y. So if you take a square root or a fourth root, you're going to get two possibilities. And don't forget that, because that can lead us into trouble. So now, this is going to come up into our constraint. Well, all right. So let's go ahead and work it through. So we have two cases, x equals 2y. And so everywhere we see an x, we're going to put a 2y. So we get 2y to the fourth. That's 16y to the fourth. Then we have 10 times 2y times y, so that's plus 20y squared. Then plus 16y to the fourth equals 3. Or 32y to the fourth plus 20y squared minus 3 equals 0. All right, well, what can we do here? Well, can it factor? Okay, that seems hopeful, perhaps. What do we need? Well, the minus 3 tells us we're going to have a plus 3 and a minus 1. They might say, or it could be a minus 3 and a plus 1, but let's try this one first and see if that works. And what do we do? Well, we need to break this up. Everything's in terms of y squared, so we have something y squared, and we need to think of how can we break up 32. Well, one way to do it is 8 and 4. I think this works. Let's check. By the way, if you're like, I couldn't do that, you have options, such as, think of this as y squared squared and y squared. You can use the quadratic formula. But let's check. 32y to the fourth, that's good. 24y squared minus 4y squared is 20y squared, and minus 3. Oh, phew, it actually worked. Okay, so what does that give us? Well, it tells us either y squared equals 1/8 or y squared is negative 3/4. Hey, good news. We can rule out y squared being negative 3/4 because you can't have a square equal a negative number. So we say, so that says y is really plus or minus square root of 1/8, and that's 1 over 2 root 2. So x being 2y, we end up with 2 points. And, okay, I think I'm going to run out of space here. I'm going to see, do I have some paper? Yeah, I've got some spare paper. So don't worry, we'll get the whole problem on the next 1.5 pages, right? Okay, so we get the points two candidate points. We have 1 over 2 root 2 and minus 1 over 2 root 2. X is 2 times that, so you get 1 over root 2 and minus 1 over root 2. All right. Good. Now, on this page, we're going to do the same thing, but x equals minus 2y. All right, so same process, we're putting it into our constraint. Minus 2y to the fourth, that's 16y to the fourth, and then plus 10 times minus 2y times y, that becomes minus 20y squared. And then we still have a 16y to the fourth, and then we get a 3. Or, rearrange, that becomes 32y to the fourth minus 20y squared minus 3 equals 0. All right, so does this factor? Well, suspiciously, I think it will. It's almost like it was planned. Now, if you're getting nervous about this particular factoring, keep in mind, this is on the hard end of what we want. We are doing hard problems for practice. On the actual exam, we tend to make sure it's not too hard, it's still doable. So don't panic. Now is not the time to panic. Now is the time to think about the processes. Think about where we're going. All right, so how does it factor? Well, I think we'll do something very similar, except let's maybe change the sign around. So we'll make this a minus 3 and a plus 1, and we'll still do an 8y squared and then a 4y squared. Let's see if that does it. So very similar, I'm just essentially changing the sign. Does that do it? 32y to the fourth, that's good. Minus 24y squared plus 4y squared, minus 20y squared, and minus 3. Good. So that gives us two possibilities. Y squared equals negative 1/8, or y squared equals 3/4. Now, as before, we can rule that one out. Y squared can't be negative. That's a little bit too complex. It's not the kind of thing that we would be doing. So that leads us to the conclusion, y is plus or minus square root of 3 halves. Okay, so that gives us 2 points. So something, comma something, and something, comma something. We have square root of 3 halves minus square root of 3 halves. That's our y values. X is minus 2 times that. So minus 2 times square root of 3 halves would be minus square root of 3. Minus 2 times minus square root of 3 halves would be a positive square root of 3. All right, so we've done the bulk of the work. We've now got to put it all together. We're making a list. So the Lagrange multiplier method is making a list type thing. It's very similar to what the last problem was. It's just that the list happens to be on the boundary. So we have the following points. These are the points at which something interesting will happen. So I have 1 over square root of 2, 1 over 2 root 2, minus 1 over square root of 2, minus 1 over 2 root 2, minus root 3, square root of 3 over 2, and square root of 3 minus square root of 3 over 2. All right. Well, how do we finish up now? Now that we've made our list, the maximum and the minimums are going to occur somewhere on this list. To figure out where, we evaluate. So, we're going to plug each one of these into f. And f is a very straightforward function. You just say 4 times x times y. So if I take 4 times 1 over root 2 times 1 over 2 root 2, what happens? Well, I'm going to get 4 times a fourth. So this is 1. Here, 4 times minus 1 over root 2 times minus 1 over 2 root 2. The 2 minuses cancel. The root 2 times the root 2 gives us a 2. There's already a 2. So again, 4 times a fourth is 1. All right, how about the other point? The next one. 4 times minus root 3 times root 3 over 2. Well, the root 3 times the root 3 gives us 3. And then we have a 4 over 2. So what does that give us? Well, that gives us 6. All right, good, good. And, all right, now what? Well, do the same thing here. 4 times root 3 times minus root 3 over 2. Oh, not 6, negative 6, right? I forgot that minus sign. And so here, again, 4 times a half is 2. And then we have the root 3's. So that gives us negative 6. So we say, aha, these are the absolute min, which is 1. And here we get the absolute max. This is absolute max. I'm sorry. I forgot to take the negative sign into account. We're near the end of a test. Yeah, it can happen that you can get some fatigue when you're taking a test. So absolute max is positive 1, and absolute min, negative 6. Whew. Okay, let's catch our breath for a second here. We have been on a journey, right? We've definitely come quite a way. Now, with that in mind, I want to recap this problem because we haven't had quite as much practice with this. Look for the equals. Something we're trying to something we're trying to optimize with a constraint. And so there's no interior. So we're really trying to build up to 2 equations, 2 unknowns. One equation comes from the constraint. The second equation from gradient of f equals lambda gradient of g. Once you have your 2 equations, 2 unknowns, the second equation usually reduces to something pretty simple. Plug that back into the first equation, solve for your points, carefully work through it, piece by piece. Make a list. Now, be careful how you interpret the list, but if they ask for a max or min, just trust them and say, that's what it is. That was our last problem. And I know we went really slow. You're probably looking this time and saying, Steve, it's supposed to take 75 minutes. But I deliberately went very slow because I was trying to explain these concepts. We could have gone much faster. And some of the problems we did it in more than one way. So don't take the time that we took on this test to be an indicator like, is this a long test? It's not. It's a test that you can do. You are amazing, and you are capable of doing great things. Don't be afraid. Practice, review, do problems. I know that's what practice is. Make sure you understand. It's not always about computation. You have to understand how to start the computation if you want to make progress. I believe in you. Good luck. I hope you do well. And then we'll get to do this again one more time. Bye.